Hello guys and welcome to my channel. My name is Milos and I'm a creator of original maps which I regularly post on Instagram and Twitter. More than a half of world's population lives in cities, and by 2050 more than two-thirds of world population is estimated to be living in cities. Now, sometimes we feel as mere bystanders in this global process. But what if I told you that you are able to map the city expansion in R for any city in the world? That's right, in today's tutorial, we will cover how you can map urban expansion of any city in the world using R. In today's tutorial, we will use satellite data compiled by the Global Land Analysis and Discovery Institute on built-up land extent and changes in the last 20 years. We will be mapping the urban expansion of Delhi in today's tutorial. As a first step, I want to show you where the data is located. Then I want to show you how you can load this data directly into R. And in the process, I will share also an easy method of downloading the data for any other city in the world. Then we will load the roads from the OpenStreetMap data to enrich our map. And finally, we will create a buffer around our map so that we get a nice circle frame. Without further ado, let's roll. And we start today's adventure from the Global Land Analysis and Discovery website, where you can find a bunch of data sets on global cover change. And one of them is the built-up land extent and change data set, which tracks urban expansion in the last 20 years. The creators of this data set are from the Institute under University of Maryland, and they use machine learning techniques to convert OpenStreetMap data into images that would allow for recognizing patterns in cover change. So in this concrete data set, what they were trying to do is find what were the patterns of human-made surface change, including infrastructure, commercial or residential land uses, such as, for example, buildings. So what they tried to do is they first converted the polygons from OpenStreetMap data into images and then back to polygons. And for that, they used the UNet image recognition machine learning method from the biomedical sciences, which is one of the most precise methods. A few words about the data before we proceed. So this data set is in a raster format, to be more precise, GeoTIFF, which means a raster with a coordinate reference system. In this case, WGS84. All layers are provided in 10 by 10 degrees formats, and these tiles can also be accessed in shapefile format, but for the purpose of this tutorial, we will be using raster files. Now, since we are talking about raster files, they're made up of pixels, and pixels here can have essentially three values. One is that there is no built-up area at all. Second, there is a built-up area, but there was no change in the last 20 years. And finally, there was a built-up change in the last 20 years. We easily access the data if we click on the link built up area extent and change 2000 to 2020, which opens up a new window. And the new window opens up showing a directory of 10 by 10 degree tile files, and unfortunately for us, they do not denote the name of the continent, country, region, or even a town that they display. The only thing that we find is a bit of a generic prefix of change underscore, followed by some series of numbers and strings, and then ending with TIFF extension. So these numbers and strings that exist in the middle, these are the latitude and longitude values of the specific tiles. I know that because N and S stands for north and south, which actually measures the latitude, and then E and W stand for east and west respectively, which is used for longitude. Essentially, this will help us identify a tile that we need for Delhi, but to do that we do need to know the coordinates of Delhi in order to choose the specific tile. So next thing what we will do in R after loading all the packages is that we will pull all the file names from this specific website, and then based on the Delhi coordinates we will search for the tile that we need. The easiest way about downloading the data from this website would be simply just to copy the link to the file we need. But in our case, we don't yet know what is the file that we want to download directly into R. So the easiest way would be simply let's scrape all the information from this page and then get all those downloadable links, and once we know the coordinates of Delhi, then we can search for the file that we actually need. So in order to actually even start with scraping this website, we first need to inspect it. So once you inspect it here, we notice that the body is highlighted when we hover over this part of the HTML code, and then once we go down and each individual part is highlighted, we find the familiar link, and we see that this one is embedded into href. So back in R we will need to parse this information from href, and then that way scrape all the possible links that exist on this website. Once we scrape those links into R, we will then determine what is exactly the file or files that we need to download. And we are back in R, where we will load several packages necessary for today's tutorial. The first one is tidyverse, which we use for data wrangling. The second is the SF package that we will use to plot the roads coming from the OpenStreetMaps. The third is the OSM data, which we will use to load the Delhi roads as well as the Delhi boundaries. Then a Terra package is a package that we can use to load, modify, crop raster files, and HTTR and XML are used to send a request to the data site, from which then we will fetch the links and eventually also the data. As a first step, we scrape all the information on the existing web links of the GLAD website, and to do that we define the link to the website itself. Then we create an HTTP request using the get function. After that, we parse all the HTML data to an HTML format, and after that we scrape that information and take only the href tags where the web links are located. Then we get rid of the first 5 outputs, which are not really web links, and finally for every link we simply patch it to this main website, and that's how we get all the links. When we inspect the rlinks object that we created, we find that there are 280 links. Of course, we don't need all of them, but this will help us loop through them once we know where exactly the Delhi will be located among these tiles. Hands down, the easiest way to get the coordinates is simply to go to Google and then type the name of your place's coordinates. And then you get the latitude measures and the longitude measures. So for Delhi, we find that latitude is around 28 north, and longitude is around 77 degrees east. This is a very important piece of information because if you remember, in those file names that we fetched, there was a label for north or south for the latitude measures and east and west for the longitude. So this will help us nail this down. And we are back in R with Delhi coordinates, but now comes the difficult part where we need to figure out what is the file name that we want to load into R. It is a bit of a hit and miss practice, exactly because we don't have specific file names that indicate either a country or a region. But what we do know is that in those file names, both the latitude and longitude measures are rounded. So in our case, the latitude, which is around 28 degrees, we should be looking for a file with 30 north. And for longitude 77 east, probably we should be looking at something for 70 or 80 east. Now, to save you from troubles, I went through some trial and error before, and I actually found that the file name we need has 30N and 70E. So what we want to do next is, first of all, let's define the coordinate system we will be using. In this case, it's the standard WGS84. And then from the list of links, we take the one that has 30N 70E. Then we use Terra to directly load a raster from this link. So this is a fantastic package because you don't need to download the raster to your drive. What Terra does, it simply takes it from that link that you provided and then loads it into R. And then finally, we will reproject this raster image into this WGS coordinate reference system, and then we will plot it. For those of you who are not able to decipher the geographic location of this raster image, the Delhi patch is somewhere in the upper right corner. So we don't really need this entire image, we only need the Delhi part, and I will show you in a bit how you can crop only the Delhi area. But before we do that, I also want to bring your attention to the values in this raster. Null stands for no built-up area at all. 1 stands for both the existence of the built-up area, but also which is newly built in the last 20 years, and 2 stands for the existence of built-up area, which is a stable one, so it was not built in the last 20 years. So we've seen how to import one raster file, but what if our city spans over 2 raster files? So I here want to just make a small digression. This is quite possible. When I was, for example, mapping the urban expansion for Lagos, Nigeria, this city was present actually in 2 raster images, so I had to download both. So here I want to show you how you proceed if you have 2 raster images, how you actually create them. So it's quite simple. First of all, what you do, you load both of those raster images, and then you use Terra to import them. But after that, you need to do an additional step, which is to merge these 2. So what you do is you just use the merge function from Terra, and then finally you do the same step as we did before. So you simply convert it into the coordinate reference system. So we loaded that large area file into R, but we essentially only need the Delhi extent. So how do we get the Delhi boundaries? Luckily for us, OpenStreetMap data has the answer. This is an open data source which collects information on continents, country, region, even town polygons. Then it also has information on roads and railways, points of interest, and other features. So this is the website where you can find your city of interest, and then if you type the name of the town followed by a country and then click on go, if this town exists, then it will open up. So this would be the Delhi area. Now the next step would be to load this data directly into R. Luckily, again, we don't need to download this on our drive. There is an OSM data package which can be used for that purpose. But this package is only used for smaller areas, and in our case, we want to fetch information for the town level, so that should be fine. Grabbing the Delhi boundaries polygon from the OSM website will essentially serve 2 purposes. First, it will help us understand if we really loaded the right raster for our case. And second, we will use that to crop the raster itself to the extent of Delhi. So back in R, in order to do that, we first of all define the city name, the same way we did on the website. So it's going to be Delhi, India, and in the next then chunk, we use the OSM data and specifically get BB So this will take actually the polygons of the city that we defined, because in the format out we defined that we want SF polygon. So we don't want a bounding box, we really want a polygon of Delhi. And then in the last step, we simply set the WGS84 as the reference system, and again transform just to make sure that this is it. So we plot the raster and then polygon as an overlay, and we immediately notice that the polygon does appear in the output. This is a good sign that we chose the proper raster, and you can use this method also for your own purpose for any other city to just check, do a sanity check before even cropping, whether you really got the raster you needed. In this third step, I want to show you 3 ways in which you can crop the raster image. And then from the fourth step, you can simply choose your approach and your object and just continue from there. So the first method will be simply to crop by the polygon that we downloaded from the OSM website. And the way we do that is first turn this Delhi border object into a vector-friendly format for Terra. So we use the vect function from Terra. Then in the next step, we use the crop function from Terra, where we first define the raster object. In our case, it's built up data, and then the Delhi vector. And finally, because we only want the area that exists within the polygon and nothing else outside of it, we need to use the mask function from Terra, which turns into null values all the pixels that are outside of the polygon area. As we can see, the image was cropped using the polygon, and now we have only area under the polygon. Everything else is set to null, so it's not visible. The second method includes using the bounding box of the polygon to essentially create a rectangular view of the raster image. Now, if you're not familiar with bounding boxes, what they are, how they're created in R, and how do we use them, please check one of my previous tutorials with the link below. So we first of all create a bounding box using the SF package, and after that we just grab the minimum and maximum latitude and longitude measures, and using these data points we then create a bounding box polygon, which we also turn into WGS84 coordinate reference system. And then we use the bounding box polygon and basically run the same thing as we did in the first method. So we declare the bounding box polygon to be a vector in a Terra-friendly format. Then we crop the raster by this bounding box polygon. Then we mask values that are outside of the bounding box polygon. And finally, we get the output, which we also plot. And as a result, R returns a rectangular shape of the raster image that we just cropped. And we come to the third method of cropping, the output of which we will use in this tutorial, and that is the creation of buffers. Buffers are circles around a certain area. In our case, we want to create a circle or a buffer around the Delhi polygon. In order to create a circle, we need to have a central point or a centroid. So we will first get the centroid of this Delhi boundary polygon using the st-centroid function in SF package. And then we will apply to this the st buffer package. Now, we do need to know the radius of this boundary polygon. So here is where it becomes a bit tricky, because it will vary from town to town how big it's going to be. And also the way to determine is not so straightforward. So again, it includes a lot of error and trial. And we do find through some error trial that the buffer around Delhi would be approximately around 28 kilometers. So it would encompass all of the Delhi polygon. If you want to create a smaller circle, in a sense, you want to crop a certain area within a Delhi polygon, then you can also decrease the size of the radius. And finally, we set the WGS84 coordinate reference system and transform again to it to make sure that we again operate in the same coordinate reference system throughout this tutorial. Let's just quickly plot this buffer together with the Delhi polygon and see what we actually got. We'll use ggplot to show how the buffer looks like around the polygon. So for the deli borders, we will use the blue color, and for the buffer itself, we will use the pink color. As you can see, the buffer is placed around the deli polygon and completely encompasses it. Feel free to play with the size of the buffer. You can increase or decrease it as you see fit. And we use the buffer to crop the raster image. First, we transform it into a vector using the Terra package. Then we crop the raster by this buffer. And finally, we mask the values that fall outside of the buffer. And we get a nice circular image. Remember, if you decrease the radius, you can also get focus on a specific part of deli. In order to plot the raster using ggplot2, we first need to transform it into a data frame with coordinates and then the value for each of these coordinates. So in order to do that, we just use the outputs of the method that you chose. In our case, it's going to be the buffer, so the third method. And then we transform that cropped file into a data frame. And we also say that it's going to have coordinates, which is this XY argument here. And then once we do that, we inspect the data frame. We retrieve data frame with three values: X for longitude, Y for latitude, and the third column is the value column, which is named after the file name. So we will conveniently change this into value. As we said, the raster holds three values. Null is no built-up area, 1 is the expanded built-up area, and 3 is the existing built-up area. Now, to make this more straightforward, we will turn this numerical values into strings. So null will become no built-up, 1 will become new, and 2 will become existing. It would be really cool to enrich our map with some additional urban features, such as, for example, roads. For that purpose, we will use the OSM data once more. Now, if you're not familiar with the way OSM classifies roads, I suggest that you check their wiki page, where you will find that all the roads and paths are lumped together under the key highway. And over there, we find that they have numerous ways of classifying roads. For our purposes, we will just focus on the major roads. So these include motorway, trunk, primary, secondary, tertiary roads, and then of course the links to those roads. Once we define the road tags, we can then proceed and query the roads from the OSM data. Again, we call to rescue the OSM data package, and we also need to create a bounding box for the area that we want to fetch. Now, if you didn't follow the second method of cropping raster, here we will again then define the bounding box within our function. Then we will create an overpass query using the OpenQ function from the OSM data. And then we will tell that query that we want a highway key where the roads are located. And then within values, we will specify our road tags. And finally, we will convert this whole object into a shapefile by using the OSM data _sf function from OSM data. To make sure that this object is aligned with other objects when it comes to the coordinate reference system, we finally convert it to the WGS84 coordinate reference system. As always, we inspect our data by plotting it using ggplot2. And in this case, what we want to make sure is that these roads are overlapping with the circle that we created. So to do that, we first define the circle itself. It's going to be in line is going to be blue. The circle itself is going to be transparent so that we can see roads in the background. And the circle is going to be a bit thicker. Now, if you followed some other steps, for example, like the bounding box maybe, or the polygon, you can simply replace the deli circle object here with your preferred object. And then we will also plot the roads themselves, which are gonna be in pink. So it looks like we got the roads right. They do overlap with the circle, but they also go outside of it. That's because we chose the bounding box as a tool here, which is in rectangular shape. And now in the next step, we will clip those rows that fall outside of the circle. You can also choose, for example, to keep them, but just for the sake of clarity, and because here the focus is on urban expansion, we will do so. Again, if you use some other method, for example, the bounding box, again, if you use the belly polygon shapefile instead of the circle, you can in the next step also use those objects, so replace just the daily circle with them. We will clip the roads using the st intersection from SF package. So for that we need to provide first of all the polygons that we want to cut, and then the next argument is the polygon that we will use them to cut. So in our case we want to cut a daily road, so we first specify them and then we specify the daily circle. Again, if you're using the bounding box or polygon, you should specify them here. And after that, we are going to plot again for the circle. Here we are using the blue color and a bit thicker. And in the second argument, we specify the newly created daily roads cropped, and they're going to again be in the pink color. The road polygons now fall completely within the circle, and the graph already looks more neat and clean. And we are finally ready to create our map of urban expansion of Delhi in the last 20 years. But before we do that, let's first define the colors for our categories. Dark gray color will be used for the lack of any urban areas. Then the yellow one will be used for the urban expansion in the last 20 years, and the blue one will be for the existing urban areas. In the ggplot2 code itself, we first want to plot, of course, the raster, which we turned into data frame previously. So we will use the geom raster function from ggplot2, and then we will provide that daily df object we created, and we will define x and y. And of course, we will fill using the cat or the category one. One more thing, I set here alpha to 1. That means that I want the colors of these to completely dominate, so they will be the strongest possible. The second one that we will add, of course this one is optional, is to add those rows that we previously cropped. And because it's a polygon, we use the geom sf function. For the roads, we use the same color as the lack of urban expansion. That's because we just want them to melt into the whole scene and to give more space to the urban expansion and to the existing urban areas. Also, we select a bit smaller size of rows so that they don't really dominate this graph. And alpha is also set to 1. You can a bit maybe play with this one and assign probably a lower version to roads. And finally, the roads will be transparent, so again giving more room, more space to the colors of the urban expansion graph. Since we want to fill the polygons with categorical values, we definitely need to use the scale fill manual function from ggplot2, where we also specify our colors to be used. The guides function is very useful for customizing your legend appearance in the graph itself. So here we say that for the fill argument, we will specify how the legend will look like. And in our case, it's going to be a horizontal one, a pretty long, so that all the labels can fit well. And it's going to be pretty thin. It's going to come on the top of the graph. And we also justify all the labels and the title as well. And it's going to have only one row because it's a horizontal one. And the labels will show up on the top of the legend. And finally, the theme. In the theme, we define how our background is going to look like, including some of the features such as, for example, legend, plot, title, or captions that we might have. So in this tutorial, we'll create simply a dark background, having the same color as the lack of urban expansion or urban areas. So that we actually have a pretty minimalistic graph where we put focus especially on the existence of urban areas and their expansion in the last 20 years. We want the legend to be a bit higher, so we want to specify a legend that is very close to the title. So for that purpose, the first value, which is X, it's going to be somewhere in the middle, and the next one is Y, which is 1.05, which means it's going to be pretty high in the plots, but making sure that we do not go over the title itself. Then we also specify the legend text and title. Here I chose a bit lighter colors so that they can be visible, since the background is going to be dark gray. Again, you can play with these options. And then for legend spacing, I chose a bit of a spacing between the labels and the legend plot itself so that it's clearly visible. And then further down, we also specified title and the caption size and colors. Again, it's a bit lighter so that we can see them on the dark background. And plot margin we use to actually decrease the space around the plot itself. We do assign null values for the left, bottom, and right part of the plot so that we shrink the space around it, but we assign one, so we give a bit more space on the top for the title and the legend themselves. And finally, when it comes to the background, we also add dark gray for the plot background, but also panel and legend background. And in the lab section, you can add some additional information. What I usually do, I just put a title, and then also in the caption, I do the name of the creator, but also the data sources so that my followers can easily find them online. And this is the final map where we show the urban expansion of Delhi in the last 20 years. As you can see, there are a lot of such areas painted in yellow. And you can also see that there are some stable areas. The majority of them are actually stable areas. You can further play with this map using perhaps a different color if you don't see this one as fancy enough. You can also play perhaps with the location of the legend as well as the font size, allowing maybe more space for your graph. And that's all for today, ladies and gents. In today's tutorial, you learned how to create a map of urban expansion of Delhi in the last 20 years. We use the GLAD dataset on urban expansion, and we also use the OpenStreetMap data, specifically the polygons and the roads of Delhi. One of the things that you learned today is you got familiar with these data sources, then you imported them directly into R, and then you also learned how you can crop these data and how you can create different forms using the polygon, the bounding box, and the buffers. And finally, you also learned how you can map this data in R. I really look forward to seeing your own use cases based on this tutorial and mapping how the urban expansion has played out for some of the cities around the globe in the last 20 years. So feel free to check the GitHub repo of this tutorial below. Also feel free to clone it, reuse it, modify it as you see fit. And I will be also open to your feedback and questions on this tutorial. So feel free to reach out to me through YouTube, Instagram, or Twitter. And if you find my work useful, also consider buying me a coffee. Finally, check some of the previous tutorials which might help you as you go through R. See you next time.